Today's lecture number 3, E512, CMOS analog IC design, and today is August 18, right? So, as we discussed, this is the book which I am following, and now the course is starting actually, right? If you get any difficulty, please let me know. Accordingly, we'll proceed because it is depending on your understanding, right? Accordingly, I try to cover. It's not about like I'm trying to, pack so many things. It's about understanding. If it is required, we can take some extra lectures also, right? So let's start from here. What is large signal? What is large signal? And what is small signal? You heard about it, right? So how to know that which signal is large, which signal is small? Any thought? You must have studied somewhere, right? This one is very simple, right? You must have studied. But I know that still people have doubt. So tell me, what is small signal and what is large signal? By the way, both the signals are AC signal, DC signal. Which kind of signals these are? We are talking about, like, we have to add something here, right? So small signal, DC signal, AC signal. Okay, so large signal is also AC or DC. So both are AC, by the way, or where there is a frequency is associated. We are talking about that. Right? DC is a different thing. Generally, DC is the one through which we are bias the circuit, or we make sure that that particular region of operation will be achieved through the given DC. Sometimes through AC also you can give that, because each one of the signal, like this signal, if I am giving to or applying to the circuit, then in reality it's a DC at a time. Look at this, these are the sample point, right? So these, all of these are acting as particular voltage over here, right? If they are, so this is AC and DC. Let's go this way. Through AC also you can bias the circuit, right? So it's not only compulsion that it's only AC, DC which can bias the circuit, but sometimes AC is small signal, large signal. If AC is large signal, then it can bias it very easily. If it is small signal, means its amplitude is very low, right? So now tell me, what will be the small signal and large signal? We know that small signal is having the amplitude is very low, large signal is very large. But which one we are going to call it small and which one we are going to call it large? Everything depends on the circuit, first of all. You can't say that microvolt is small signal, millivolt is small signal, or volt is small signal, right? It is depending on the circuit. Let's assume that there is a circuit. I believe all of you understand this triangle. If it is triangle, it's generally, if nothing is written, its amplification is 1 generally. But if something is written, let's say I am writing here 10, means the gain of this circuit or this amplifier is 10. If I am applying here 1 millivolt sine wave, what will the output? 10 millivolt sine wave. Okay, no problem, right? But what if this is 1 volt and if I apply here 0.5 volt sine wave, what will be the output?
Like it will get clipped at once.
Correct, right? So this is very simple. Might be something like this, right? It's clipped at 2 points. One is this point and one is this point, right? This will be VDD of 1 volt and this is ground or 0 volt, which is given to this circuit. If it is 5 volt minus 5 volt, it will be there only. So you have to find out the point where this is not getting clicked off, because we want to find out, let's say, gain. I'm interested in finding out the gain. If I know this signal, if I know this signal and I do not know this one, right? I need to find out because it's inside the triangle. I wrote it, that's why you know it's 10. But if it is not known to me, how can you know that the gain is 10? If I am applying 0.5 volt, it's getting saturated. If I divide it, it looks like gain is 2, right? Because the maximum value is 1 volt. But that's not true, right? So how much value is required to be given over here to see the exact gain? If I want to find out the gain, what value you are going to give it as an input where it's not going to get saturated? If I want to have signal like this only, right? How much? 0.1, right? Is it correct or no? Because 0.1, it might be like this. It's absolute signals, right? So then you have to adjust something. You have to give 0.1 sine omega t plus extra 0.1, right? DC is also required in this case to get exactly like this, right? So or sorry, keep it here 0.5. That's the correct. Okay, it was my mistake. If it is around exactly VDD by 2, then you can have the full scale thing. If I am giving anything beyond this 0.1 and if the gain is 10, I am going to see the saturation. So this is untold truth in any book, but it is understandable by each one of the engineer that whenever you are giving an input which is not getting saturated, till that point it's small signal. For this circuit it's 0.1 volt. That's a small signal. But for 100, this might not be true. It's 10 millivolt, which is small signal. If it is 1000, it's 1 millivolt. That's the small signal, right? So this is how you determine. But this might also happen that you want to apply here the square wave, which is of course this square wave itself is a large signal, right? Input is itself is saturated, right? It's going between logic 0 and logic 1, or 0 and VDD, or VDD and VSS. So then the output is also VDD and VSS only. Those signals are dealt with digital circuits, right? And all digital circuits generally dealing with large signal, not small signal. So that is the main difference. As we declared, this course is all about designing an amplifier. At the end of the course, you should be able to design operational amplifier, the whole circuit op-amp inside the thing. Means you should know that we are going to deal with small signal. If you are going to apply large signal, you can of course apply, there is no problem. It is going to give you large signal as output, right? So this is one term. I believe now there is no problem. Large signal and small signal. There is another thing which we are using very rapidly in most of the modern books. I am not saying the books which are written last century. So if you are reading last century books like Sidra Smith and other Boylsted, those are very good books. Those are actually the classic books. But the current book, which is Behzad Razavi, so if you read that, you will understand he is going to use word called rail to rail. Do we know what is rail?
Like when we design a circuit, so there is generally a VDD, like a whole line, then there is the transistor in between, then there is the ground line. So that rail is
Yes. So rail is equal to either plus side V supply or maybe minus side V supply. So I can keep lots of circuit over here, plus V supply and minus V supply, right? I'm writing plus and minus V supply. It is general. It might be for BJT, it might be for any circuit. So V supply and minus V supply are actually, this is the way we are connecting, right? So this is no. So this is a rail to rail, and this is known as positive rail and this is known as negative rail, right? So positive and negative rails are the one which are treated as VDD and supply and ground. Right? So this is another word which are very popular and which is used. So sometimes we want to have rail to rail output. Have you heard about this word ever? Rail to rail?
Yes.
Where did you hear this?
Some message we have used like when they tell that this is the highest voltage and the lowest voltage.
Okay. But people like the circuits which are going to give you rail to rail output. It means there is no saturation. Usually what happens when you are looking at the output, before VDD and ground, so this is VDD and this is, let's say, ground. Actually the circuit is getting saturated much before VDD and much earlier than ground. This is happening because of lots of problems, because of some threshold voltage and other things are there. So it will not reach exactly VDD. So we have to make circuits which are reaching rail to rail or having full swing. This circuit is like red color is rail to rail, whereas black color output is not rail to rail. Some people also would like to say or call this one as full swing, or sometimes you are finding the swing also. What is the overall swing of this circuit? If it is full swing, means VDD, that is a base circuit, and we are using the entire availability of the voltage, right? So of course we know that none of the circuit will give amplification beyond its rail, right? So you don't go beyond that, so it's going to get saturated. These are the simple terminology which I want to tell you. Okay, so now before going into transistor as an amplifier, let's go NMOS. So this is true for PMOS also, but you can learn it through NMOS as well. So NMOS as a switch, wherever in any book, if you are seeing this symbol, understand that the 4-terminal body is connected to ground in the case of NMOS, and in a case of PMOS, this is always connected to ground, VDD. So, by the way, why we are doing this? Why we are doing this?
I think it is because of body effect.
Body effect.
I don't remember that.
Okay, we will talk about body effect, but yeah, that's the correct answer. Body effect, right? It's not going to give you body effect. It will give you better output, and voltage will be, threshold voltage will be better in that way. And generally these are the stable voltages which are not moving here and there. That is also one of the things. Otherwise this is also acting as another source of input, right? So all 4 inputs are there. From any side you can give input, sine wave, right? Look, there are 2 things, biasing, and another thing is the input. So I am talking about the sine wave input. The sine wave input can be going from anywhere. Even this ground is not completely ground. Actually, it looks like this one. If you have seen it, there's 0 volt. If you look at the oscilloscope, you will see that it's not exactly 0 volt. It's moving here and there. This is the sometimes device noise, because of the noise of the system it's coming. This might be in the range of, let's say, microvolt. So 1 microvolt noise, is it significant for you or no? How to know that 1 microvolt is important or not?
Depends on the type of input and what
Input is this one, right? Right. Let's say I am not giving any input. and this is acting as an input. So noise is an input, and at that time, if this is an amplifier, the circuit is an amplifier. If the gain is 10 raised to 6, this will reach directly, to VDD, right? So it depending on, you have to understand the severity as you are going for higher gain. Not 100 dB, anything is possible in 180 nanometer and any technology, right? So that's not true that you can't achieve certain, gain or frequency. One just terminology, you know about this one, FT of the device. Yes or no? So FT of the device is very important term. So the device which is given to you, it's the actual word is transit frequency. They call it transit frequency. This is all device people are using it. So it's, if I am looking into frequency with respect to, let's say, gain of single transistor. This is for single transistor. No load, nothing. Single transistor. So its own gain, which is known as, this particular thing is known as the intrinsic gain. And this particular frequency is known as FT. This particular frequency is known as unity gain bandwidth, or this is not so much important, but FT of the device is very important. FT of 180 nanometer technology is almost, for your case, maybe around 150 gigahertz. Okay. So for 130 nanometer technology, that FT of the device is almost 400 gigahertz. For 65 nanometer, this is, so as you are increasing, so this FT of the device is getting increased. Why is it so? Why do you think it's going to increase?
Low distortion and
Hmm?
if FD is higher, low distortion and
1/2 pi CGS value of FT.
So frequency is depending on 1/2 pi times RC, right? Generally, we do not like this R term. This 1 by R, we are going to call something called transconductance, right? So GM by 2 pi C. GM is the transconductance of the transistor. Maybe in detail thing we are going to study, in next few slides. Okay, maybe today or tomorrow, how the transconductance and other things are getting derived. But two things are there. Right now, this GM is still, difficult to predict right now for you people. But look at the capacitor. As you are decreasing the channel length, means earlier you were at 180 nanometer, then you are going at 130, 90, 65. The thing is, the channel length is getting decreased. So if channel length is decreasing, the effective capacitance is increasing or decreasing? Should be decreasing, right? It's epsilon A by D. So distance is getting reduced, so capacitance is getting, right? Okay. So I made a mistake then. Capacitance is going down. Yeah, capacitance is going down, right? No. There are two things, right? Epsilon A by D. So area is also getting decreased. Area is significantly decreasing compared to distance. So capacitance is going much lower, because for this case, if I am not wrong, 10 femtofarad, that's the capacitance of this one for single transistor. In this one, it was 2.5 femtofarad. So these are the numbers from, like, I'm writing for the, UMC technology or TSMC. These numbers are changing, so no need to remember these numbers. The thing is, it's getting reduced. So if the capacitance is reduced, then the bandwidth is actually getting increased over the technology side, and this is because of the area is significantly actually reducing compared to the distance. Right? There are two parameters. So this is the thing which we call it FT of the device, right? So FT of the device is one of the important thing, right? Now understand one thing. If somebody will ask you, like this is the question Santosh asked me in the morning. I gave him to design one op amp with 1 gigahertz frequency and 180 nanometer. He's saying, is it possible? What do you think? Is it possible? Look, FT of the device is almost like 200 gigahertz. Of course, 1 gigahertz is possible after so many stages and other things. Right? In my opinion, even you can give go till 30-35 gigahertz also. 180 nanometer technology. As you're going down, yeah, of course, you can try for even terahertz, and people are doing it. All communication people, right? So depending on the FT of the device, you can determine almost like thumb rule might be like divide by 100, it should work. The bandwidth wise, I'm saying the bandwidth. Gain as much you want, you can achieve, no problem. 100 dB, 200 dB, no problem. Right? There are some techniques through which you can achieve it. But as you are increasing the gain, 100 dB. So if it is 100 dB, how much in linear scale? How much in linear scale? Right? So 100,000, that's a linear scale, right? So it's 20 log, right? That's the dB. It's very simple, it's 10 raised to 5, right? What about 106 dB? How much is the gain? That's the mathematics. 6 dB is very important term. Always remember 6 dB is equal to how much? Punit. These numbers has to be in your fingertip. Multiply by 2. Because, right? So 2 makes 3.14, right? So multiplication will give you 6 point some number. So approximately it's 6 dB. So 6 dB becomes double. So this will become 2 times 10 raised to 5. Okay, very quickly, can you tell me what is 34 dB in linear scale? How much 40 dB? 100. 100 is 40 dB. No need to write down. 100 dB is equal to 40 dB is equal to 100. You agree? Look, this is very simple. 100 in linear scale, right, makes 10 raised to 2. So 20 log 10 raised to 2 will give me only 40 dB, right? So it is very simpler one, right? So this is 40 dB. 6 dB going down gives me 34 dB. So how much should be the value over here? 50, right? Because minus 6 dB is divided by 2, right? The same way you can find out. So there are many numbers. When you are actually in analog, you are dealing with dB, lots of dB. If you are going in communication, people don't like this, they like dBm, right? Then you have to follow that number, so dBm becomes in power, right? So but we are going to deal with dB. So these are the numbers, you have to keep it on fingertip. If you are learning with some communication guy, so that professor will definitely teach you to keep all these numbers dBm on your fingertip, right? So please be aware that the journey becomes very difficult sometimes. If I am asking you to design, let's say 90 dB, and if you are getting 84 dB, you might say that this, sir, it's 6 dB. But it's not 6 dB is exactly, this is on log scale. So it's, you have achieved actually half. So it's a long way to go. The 6 dB is more difficult than reaching just 84 dB. Right? So anyway, now there is something called turning on voltage. whenever you are using a switch, there is a gate which is going to make this particular transistor in on mode. When I am saying on mode, it is no.
Sir, हमारी elective class की.
So when it is on, then there is a direct connection between input and output, right? So this is called, the on state. Off state is the one when it's open, or you can say that on state will have the minimum resistance as low as 0. In off state, it has to be high as infinity, right? The same thing we are expecting from this switch. When the gate voltage is enough, right, something more than threshold voltage, then whatever the voltage is available at source, it will be available at the drain, or vice versa, because drain and source are interchangeable. Generally, source has higher lower potential than drain, right? So that is how it goes. So accordingly, you can determine what is drain and source. So this is the turning on voltage, which has to be applied to gate voltage. Now, what will be the equivalent model for the transistor as a switch? So as I already made over here, it has to be like this. This is like earlier thing was ideal, but in reality, there has to be some on resistance and there has to be off resistance. So let's agree on two more things. Wherever you are seeing anything less than 1 kilo ohm, you should not read anywhere kilo. If kilo is there, then you should understand that it's high impedance. And wherever you are reading less than 1 kilo ohm, it's low impedance. This is just a thumb rule, okay? These are the things which will be useful for your designing any analog circuits. Still, I am saying these numbers are not given in book. So, and these numbers are valid till almost like whichever technology I use till 14 nanometer. This is working. Okay. So if you are going below, then you have to find out your own number. But till that, this kilo ohm is actually the big number. So when I am saying there is a switch, if it is getting on, the on resistance has to be less than 1 kilo ohm, as low as possible. If it is 100 ohm, very good. 200 ohm, good, no problem. Still, it's a low impedance because you can't get rid of this resistance. It will be there for sure, right? And for again, so the R of resistance, in that case also there is a connection. So R of resistance has to be very high. So there are two terms you might be seeing in the book, high and low. So high and low are defined like this. In same way, you can define it for GM also, because GM is the one where you are going to deal that. So it's exactly 1 by GM, that resistance which I was talking about. So that 1 by GM has to be opposite then, right? So anything less than millisiemens or going beyond that, accordingly you can find out high and low, right? So this is the model. What is the limiting factor of speed? So limiting factor of the speed is coming from FT of the device, right? So FT of the device, which is transit frequency, this is going to limit the overall system performance, because lots of transistors will be together, where you are not only talking about these things, but other things will also come. Okay. There is one more thing which is very important before going to the course, where some complicated terms will be coming. But before that, you should know this. What are the parasitics? We talked about this, right? Last time, just so what are the parasitics? How it's generated? By looking at the circuit, can you tell that where are the parasitics? Okay. Parasitics we know. Everyone know, right? Yes or no? Huh?
No, sir.
No. Okay. What could be the parasitics? Okay. So first understand, like one of my friend, when like I was in BTech third year and I was not understanding parasitics. So he was saying, देखो दुनिया में भूत होते हैं, दिखते नहीं हैं. So this is something like this. Parasitics are not visible, but they are there. And I am talking about parasitics, resistance, inductors, and capacitor. Sometimes some people call it RLGC also. Rather than calling it RLC, they are calling RLGC. That's the actual correct way. Right? So those are available at particular situation. We need to see the situation. Situations are as follows. If there is a path, right, from point A to point B, if I am drawing a wire, wire will have some resistance, right? Or this point, if I am applying, let's say, square wave, this will reach after some time. It is as good as if I am keeping the pipe from south campus to north campus of water. So water going from here to that side will take some time, maybe 1 minute, 2 minutes, whatever, from going from here to there. It is happening because of the resistance in between the path. It's because of capacity. Means it's dynamics, fluid dynamics is also there. So it is same thing. What mechanical people are also doing it in fluid dynamics. This is also the fact that there are parasitics of resistance and capacitance. So wherever you are seeing any path, I am drawing a big resistance, but in reality, lots of resistances might be there. It is coming because of two different ways. One is called lump parameter, and this is another called distributed parameter. So these are communication people are generally model their transmission line. If you heard the word called transmission line, right? They're sending the signals, right? Even from that HDMI, all these things are known as the transmission line for them, and they're transmitting frequency, very high frequency, sometimes packets, large signal. So all these things are going through that, and these are the lines which has their own resistance and definitely capacitance, inductor, many things will be there. But the first thing is resistance will be always there if there are two points, and if you're connecting through a wire, there is always a resistance. It might be distributed, it might be lumped. Distributed means multiple like this. So many are there. This is parasitic resistance, which is between two parts. And we know the characteristic of capacitance, which is derived by the driving point impedance of capacitance. What is the driving point impedance? ZC? 1 by G omega C, right? Okay. So when to use Laplace and when not to use Laplace? He told, are these both same or different?
So when we talk about sinusoidal analysis, means on
Both.
0 omega frequency, then we use.
No, still it's not giving the correct answer. I'm saying, can you write down both the equations are correct and same or different? So this is correct one. I wrote the correct one. In your school, you must have studied the first one, not this one. This came afterwards. So what was the reason? Whenever if you have studied, let's say, signals and system, most of the places they are dealing with G omega. But when you go to control system, this becomes 1 by SC. If you go to communication, again you come to 1 by G omega. So which one is the correct one?
Sir, we write the one upon J omega, consider that the system is stable. I'll consider the ROC.
This is correct, but this is the derived definition. What is the fundamental thing? This is correct. The fundamental thing is the initial condition. The most fundamental difference between Fourier and Laplace. By the way, Laplace was, supervisor. He is supervisor of Fourier, and Fourier has derived this formula before Laplace came. If you go to one place in Paris, so one place is Laplace and next place is Fourier, the next stop on metro. There the equation, both the equations are written. The Laplace metro station, you will find Laplace equation, and that side its equation is written as, the Fourier has another equation. But the main thing is, if you look at this, when they have started, now they are not following. When they have started, the first metro line started from the place called Laplace, when they started. And then the first stop was Laplace, not because Laplace was the supervisor, but Laplace has the initial condition as 0. That was the real reason when they started this metro line almost 100 years back. So Laplace is, because initial condition of all Laplace is 0. Then and then this is true. Otherwise, for larger spectrum, Fourier is correct. Right? So otherwise, S equal to sigma plus j omega. Right? So that sigma is 0 over there. Right? So those are the things. Right? So this is, I am going to refer this equation for the fundamental reason. So 1 by j omega c. Right? So what does it indicate? As you are at low frequency, what's going to happen to this impedance at low frequency? At omega equal to 0, Zc, can I call this one as infinity? And omega equal to infinity, Zc goes to 0. Right? These are the numbers which are not purely infinity and purely 0, because there are lots of other things are there. But let's assume that this is infinity and this is 0. If it is infinity, this is as good as open circuit, this is short circuit. So capacitor or its impedance gives you, connection between two points only when you are at high frequency. Let's call this regime as high frequency, and let's call this regime as low frequency. Right? So if you are at high frequency, then, so this is the first thing, to make this capacitor active or becoming the candidate as a parasitic, it is only possible at high frequency. Right? We need to find out the value of this frequency, maybe sometimes kilohertz, sometimes megahertz, it depends. Right? And if there are two plates, if you are saying, I should write down two dissimilar plates. When it's two dissimilar means, let's assume that there are two wires are going from here to there. There are two wires. I'm sitting in, it's a laboratory. I'm applying here 1 volt sine omega t, right? So, and it's, let's say, in gigahertz, high frequency I'm saying. This is also 1 volt sine omega t, same signal, 1 gigahertz. Then these two wires are not going to talk to each other. Means there is no capacitor. Whenever I'm drawing this one, it's a parasitic capacitance. However, if one side is, let's say, ground, so there are two plates, parallel plates are there. One side there is high frequency, another side is not there. It doesn't matter. Another side also, it might happen, there might be the frequency. Depending on the distance and all, there might be distributed or lumped capacitor. You can assume whatever you want to assume accordingly, depending on how much length of this transmission line. So in that case, if this is a sine wave, all these capacitor are at particular frequency they are going to be shorted, right, with the low impedance value. Right? Some frequency will be there where impedance is low, and it's going to get the short between that particular point to this particular point. Means this ground will not be ground, but it might happen then you will see that the frequency of 1 gigahertz is reflected over here, right? So how to get rid of this? Have you seen ever such kind of thing? You cannot use this naked wire in the laboratory. Do you use those wires or you use something else? So how to get rid of it? But the trick is, this was one of the greatest invention happened in history, almost like I would say in 1988 when electrical engineering has started. During that time they have invented this by three different scientists, Bethlehem, Nickel and Cobalt, that you keep one more line over here which is actually grounded and keep one more line over here which is grounded. So whatever is going here, let it be going here and getting grounded. There is no problem, right? It will be actually the signal or whatever is there, it's going to get grounded over here. It's not going to disturb the other line. By the way, those three scientists' name, if you write it down together, this is called BNC. So they made this probe. Outside is always grounded. If you open it, you will see that outside it's actually connection of this. It is like this. Something they created some copper outside and which is grounded and connected through something like this, right? Where outside this steel connector is actually ground, which is connected to oscilloscope or whatever is there, and that goes to the chassis of that particular instrument, and that chassis is actually grounded, or it goes to the earthing, right? So it's the least path which is going to give you all the noise, which is going to be grounded, right? So that is how it was created, to get rid of these resistance and capacitance. However, these will also have some RC. As I told you, you can't get rid of everything, and because of RC, because of these RC, the whole thing is getting limited. Means if you are using, let's say, BNC, which is look alike to steel color, right? Steel connector is there. After connecting this, there is something written over here, something like, if it is 1x probe in our laboratory, generally it's written 50 ohm in shunt with 1 picofarad. If you go to 10x, it is 1 mega ohm in shunt with 1 pico. 100x, 10 mega ohm, 10 or 15 pico, something like that. As you are going high, by the way, this 50 ohm 1 picofarad in shunt in Chandni Chowk available at 10 rupees. However, if you are going into 10 raised to 5x, that is almost, if I am not wrong, 30-40 lakhs. That's the price of that one. In our laboratory, 10x is available, which is costing something like less than, I would say, 300-400 rupees each probe. Generally, one 10x probe is coming free with the one oscilloscope. So all those are free, by the way, or included in the price. But this is also one of the field where only one company in the world which is ruling actually. You see, Agilent, or so the new name is actually Agilent was taken over by Keysight. Even though they are writing Agilent, but Keysight is the best company in the world which is making these probes. Only they are designing probes just to make sure that this overall RC gives me better bandwidth. So that's the whole research, right? Because if I am applying 1 giga, if I am applying, let's say, 10 giga with this BNC, you can't see that. You need something else which is known as the next level of connector, which is called SMA, sub miniature version A, which can go till 18 gigahertz. Then SMB, SMC, and many other things came after BNC. Like after almost like 150 years, these things were like came. But this is all research is on bandwidth, so that you can see the result with minimum value of capacitance, minimum value of resistance, which are not visible and which are parasitics. And of course, whenever you are opposite of that, if you are going at low frequency, which is the regime of inductance, right? Right, where low frequency is the regime where inductor is there, right? But you have to make the loop to get that field. So similarly, like inductor is available at low frequency, you need to be careful of that. That is also making the notch at the lower side. Means high pass and low pass. So lower side you will get worst performance if inductor is there, or you won't see anything, right? So those are the things for parasitics. Maybe rest of the things will start. These are also supporting